Let's see. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. Welcome back. How's everyone doing today? Good. Have a good spring break? Good to hear. Yeah, I actually feel pretty recharged coming back. I actually did take quite a bit of time off. Took my son to the zoo, hung out with my parents a lot, so it was a good spring break. But now we're back. Now it's time to kind of sprint towards the end here. Okay, and so with that, today we are doing our next OpenFOAM activity. So we did OpenFOAM activity one before the break. That was kind of our first taste of OpenFOAM. Basically, just kind of just getting our feet wet, just getting used to how OpenFOAM works in general. Today will be the first time where you actually will be making a lot of changes yourself. So in activity one, for the most part, we were just kind of just looking at the example, just kind of taking a tour. That's kind of the way I described it. I had to do some small modifications in the problems afterwards, but nothing too big. So today, for the first time, we'll be making our own geometry. We'll be making modifications to the boundaries and the boundary conditions. So you'll kind of really get a chance to kind of try OpenFOAM out. Because it's OpenFOAM is very similar to how I would describe computer programming, although it's not exactly programming. You kind of have to use it, you kind of have to practice it in order to really kind of get good. You really just can't stare at examples and hope to really get good at OpenFOAM. So today will kind of be your first chance to do that. Okay. So the instructions for this activity are much lighter than the previous ones. The previous activity, I kind of walked your hand through the tour of OpenFOAM. Today, I'm kind of leaving a lot of that up to you. So I'll describe to you in words what you need to do, but it's going to be up to you to kind of implement it and make the changes yourself. Okay. So with that, a lot of today, well, my vision was that, I think more people would be here so I can kind of help them through it. But, we'll kind of go with what we have, and then we can go from there. The other thing that this activity kind of introduces at the end is a little bit more on the post-processing side. So, for activity one, we went pretty light on the post-processing. We basically just I basically just showed you how to display the contours for velocity and pressure. Today we'll get a little bit more into kind of what those actually represent, how to actually talk about them in a technical report, as well as some additional things you can do with the post-processing, like creating a line graph and doing a mesh convergence test, right? So these will be important because you're going to need to do these on the final project as well. Okay. Okay, so that's the plan for today. I think other announcements that I have. So remember, homework 4 is out there. So remember, homework 4, that has to do with kind of the stuff that we were talking about the week before we left for spring break. So that is due end of this week. So just make sure that you guys are working on that. The problems don't take too long, but the first time you do it, it is quite a few steps to do with the simple algorithm and with the pressure correction. So make sure you give yourself enough time to work on that homework. If you haven't started already, then make sure you kind of get started on it this week, just so you have a chance to ask questions in office hours. Okay. Any questions I can answer before we get started? Okay. All right. So let's go and get started. So this activity, I call it a blocked channel flow. So basically, we're going to be having this channel here. There's going to be some blockage in the middle here. It's going to be square shaped. We're going to have flow coming in. It's going to be coming in through the inlet here on the left. It's going to be forced to go around this blockage. And so that's going to create some very interesting kind of flow patterns. You see quite a bit of vortices around here. And then it's going to go out the outlet on the right. So it's a single inlet, single outlet. This is a pretty typical, what I call internal flow. You can set up a situation with pipe flow very similarly to this, and we'll see how this is an open foam. Okay. Okay. So like I mentioned that, actually, if you can hit the light too, just so that we can, it's a little bit easier for people in here to see. Thank you. Perfect. Okay. So just like I mentioned before, for this activity, we'll be taking the training wheels off a little bit, and you'll be kind of responsible for doing a lot of steps on your own. But I will kind of outline kind of the overall steps that you would typically do. Okay. Okay. So let's kind of bring this over here and bring the terminal over this way. Okay, so typically when you create a new OpenFOAM case, the way that you typically go about this is that um, you kind of very rarely create a case from scratch. A lot of times, you're going to use another case that you have written, or maybe an example that OpenFOAM has made already, and use that as kind of like a starting point, or using that as a template. Okay. So that's what we're going to do here. So we're going to use another case that we've done before. So if you have the cavity flow from last time to use as a template, that would be great. Okay. Okay. So first thing we're going to do, and so you can see here that I'm in my Ubuntu here. I'm in a folder here called OpenFOAM cases. The only folder that I have here is for the cavity flow, which is the activity that we did for activity one. Okay. So first thing I'm going to do, I'm going to create a new folder here that is going to house our channel flow. So I'm going to do an mkdir command. So that's going to create a new folder. I'm going to call this channel underscore flow. but you can call it whatever you want. That's just the name I'm choosing for that. Okay. And so you can see here that we've created a new folder called channel underscore flow. And then what we're going to do is we're going to copy the important files from our cavity flow into channel flow just to serve as a template. Okay. Okay. So first thing I'm going to do, I'm going to go ahead and CD into the cavity flow. Okay. All right. So yours may have results. I've already kind of cleaned this, and so if you have results in here, so if you have um, different numbered folders other than zero, you can just enter foam clean case, right? So remember that's the command that you can use to kind of reset your case to kind of default. Okay. All right, and so you should be left with just these three folders here. Remember the zero folder, the constant folder, and the system folder. So let's copy all three of these into our new folder so that we can use that as kind of a starting point for our new OpenFOAM activity. Okay. All right, so I'm going to do a CP command. So remember, CP is copy and paste. I'm going to add a -R modifier to make sure that we can copy folders. Okay. And I'm going to copy all three of these folders. So I'm going to do zero, constant, system. Okay. So, one thing I think this is probably the first time that we've done this, but you can actually copy multiple files and multiple folders from the CP command, right? Um, the only thing is that, the way it works is that if you're going to copy multiple things, right, you can list as many things that you want under the copy command. Um, the only thing that you have to make sure is that wherever you want to copy them to, that's going to be the last location in the copy command. Okay. So we're going to cp-r zero constant system. That means we're going to copy all three of these folders, and we're going to copy that into our new channel flow folder. So I'm going to do dot dot, right? So dot dot is going to get us into our parent folder, and I'm going to copy that into our channel flow folder just like that. Okay. So this command is going to copy the zeros folder, the constant folder, the system folder into the channel flow folder. And then I need to add this dot dot here because that channel flow folder is one level up. Okay. Okay, so let's go ahead and enter. Okay. It happens very quickly just because there's not that many files there. And so let's go ahead and CD back into our parent folder here. So let's do CD dot dot, and then let's do CD channel flow, right? We hit an LS and we can see that we have our three folders here, zero, constant, and systems. And so these are copied exactly as they were from our cavity flow. Okay. So this is typically what you're going to do when you create a new OpenFOAM case is that you're going to use another one as a template. It's not always going to be the cavity flow. Just we chose the cavity flow as a template this time just because it's pretty similar to what we're going to do here. But let's say that you're doing a 3D simulation, then you would maybe use another 3D case as a template for this one here. Okay. But this is going to be our starting point for this activity here. Okay. All right, any questions on this? Everyone able to kind of copy the other files as a template? Okay. All right, so let's go ahead and start modifying the files. And so this is where I'll kind of leave it up to you guys. Okay. All right, so where we're going to spend most of our time is in the block mesh dictionary file, right? So this is where we're going to specify the geometry and we're going to specify our mesh. Okay. Okay, so let's go ahead and CD into our we'll CD into our systems folder. Okay. And then let's open up the block mesh dictionary file inside a text editor. So if you want to do it all within the terminal, you can do vim block mesh dict. Okay. Or just because we're going to be making a lot of modifications, it might be a little bit easier just to use a text editor in Windows. And so we can open up the folder in our Windows Explorer. So we do explorer.exe dot. Okay. So remember, that's going to open up our folder here in Windows Explorer. And you can open up block mesh dictionary here in let's say Notepad or something like that. So maybe you can double click this, open up in Notepad. Okay. All right, so now we can modify the file here. So if you're comfortable doing it in Vim, that's perfectly fine. But just because we'll be making a lot of changes, and since this is kind of our first time, then feel free to use Notepad if you want as well. Okay. Okay. So the first thing that we're going to do is we're going to specify the vertices of the geometry. Okay. So if you remember from activity one, right, the first thing that we looked at was that we had to define the vertices that define our geometry, right? So for our activity one, right, we had our cavity float, which is simply just a square cavity, right? Where this is node 0, this is node 1, 2, and 3. Okay. And then we had a matching set of vertices that were just slightly in front of this or slightly behind this because we had to make a three-dimensional geometry. Okay. Our geometry in this case is a lot more complex, right? And so we have a lot more vertices here. In fact, I counted them for you. There are 20 vertices in this XY plane, right? So our first step is going to be to list all these vertices into this section right here under vertices, okay? Okay, so first thing we're going to do is we're going to go ahead and delete all of these vertices here because that was what we used um, for the cavity, right? So let's go ahead and just backspace all of these here, okay? And then we're going to start inputting the vertices that define our channel flow here, starting from 0, and we're going to list them in order according to the numbers that I've listed for you here, okay? Okay, and if you kind of follow the logic here, you can see I've kind of started in this bottom left corner of the channel, and we're just progressing counterclockwise around the channel there, right? So our first point here is going to be 0, negative 0.5, right? We need to add a z-coordinate because remember, OpenFOAM requires everything to be in 3 dimensions, and so we're going to set a z-coordinate of 0, okay? And so this is going to be vertex 0. Okay? Our next vertex, just going around the horn here, is going to be 0, 0.5, and 0. Okay, so 0, 0.5, and 0. Okay. All right, so if you're just joining us, today the plan is just to do OpenFOAM activity 2. So the difference between this activity and the first one is that I'm not going to hold your hand throughout this entire thing. I'll kind of get you started a little bit, but it's going to be up to you guys for the most part to kind of implement everything yourself. Okay. So if you haven't done so already, definitely go to the Canvas site, download the PDF for OpenFOAM activity 2, and we're just kind of getting started here. Okay. Question? Yes. So is that all we've done so far? So far, all we've done was that we copied the cavity folder into a new one. So we created a new directory here I called it channel flow, and I copied all the files from the cavity flow, and then we're modifying the files inside our new channel flow folder. Yeah. Mhm. Okay, so why don't you guys go ahead and start working on that. So you have a lot of vertices to write. So I'll kind of leave this up on the screen just so you can see. But there are 20 vertices here I call this kind of the foreground. And remember, we need to add another set of 20 vertices in the background, which is going to be the exact copy of this list of vertices, but with the z coordinates slightly offset. Okay, so in total, you should have 20 entries here, or excuse me, 40 entries in this vertices kind of section here. So why don't you guys go ahead and get started? I'm going to go ahead and make my rounds just to kind of catch everyone up, make sure we're all on the same page. It's going to take a little bit of time for you guys to type out 40 different vertexes. Okay, and if you finish that early, definitely feel free to kind of move on. There's still quite a bit more that we have to implement here in the block mesh dictionary file. But I'll be making my rounds right now just to kind of make sure everyone's on the same page. Okay. Okay, and if you have questions on Zoom, just leave it in the chat. But and I'll come back around for that as well. Okay. Yeah. Open case? Yeah. What is that? It cleans it, right? Yeah. Because shouldn't I just have 0 system constant, but I still have right, so small clean case will actually clear all your result files. So remember, 0 that's your initial conditions. After you run the simulation, it creates other folders for other times. So 0, 0.5, 1, 1.5, like that. So it deletes all of those, but it looks like these PNG files were maybe images that you may have created. So it's not going to touch those. It only touches files that. Okay. Yeah. So you can probably just leave those PNG files. Copy just the folder. Yeah, I think that's a good. Okay. Let me put that one up there too, just to. I think that one's probably a bit more useful than the block mesh dictionary file. Mm-hmm. Yeah, so this is the command to kind of copy everything. Okay. How you guys doing? Good. Good. Are we good?
I think, you know what the flashback?
Thanks, doing. All right, good. Thanks, progress. A lot of Okay, okay. Yes, you want to clean that line. Or you don't have. Basically, we're gonna copy basically the zero folder, constant folder, and system folder. Copy that into it. Yeah. That's what it is. Progress, good. Let's go, guys. All right.
Does it matter?
Oh, yeah.
Does it matter, what border you like to it?
It does, yes. So I definitely recommend keeping with the order that I have here on the PDF. So starting at this, with 0, negative 0.5.
Oh, and then following that line.
Well, so each vertex there has an index to it. So 0, 1.
Oh,
2, 3.
okay.
So I would definitely put in that order.
Okay, sounds good.
Yeah.
I didn't see that.
Yes. So you can use whatever order that you want, and you have to kind of remember which order that you're using. So just to make things easier, I think just using that order.
Okay.
Yeah. All right.
Thank you.
How's it going?
Not bad, just going to that.
Got it.
Just trying to see that, so that's just the CV she's copying.
Exactly. Yeah.
Thank you.
All right. How's it going, Zoom? Let me see. Okay. Chad, yeah, there are requests in the class here to see the Ubuntu stuff. Were you able to kind of see what you needed? Good. Yeah. Jonathan, yes, you can add comments to the block mesh dictionary file or any OpenFOAM file, just like MATLAB. But then the way that you add comments is actually slightly different because OpenFOAM actually uses the C standard. So to add a comment, you would actually need 2 slashes here. So 2 slashes will make a comment. So everything past that will be ignored by the code. If you want to add a large comment, you can add a slash and a star, but then you would need to close it with that slash and star, just like that. Yeah, but usually I just use the double slash. That's the kind of easiest way to add a comment. Yeah. Yeah, I would definitely use the comments just to help you keep track because there's a lot of vertices to add here. And so adding a comment there to kind of tell you which number it is will definitely help a lot. Yeah.
Although those dashes on the end are for that's a comment.
Exactly. Yeah. So technically you don't need these, right? And so, oops. And so the code will run just fine without that comment. But I find it useful just because you're adding a lot of points, and so it's useful to kind of keep track of the numbering for each one.
Do you need like a certain amount of spaces on that, or is that just to keep it organized?
It's just to keep it organized. Yeah.
Oh.
Yeah. So as long as it's within these parentheses here, it'll all count the same, and then it uses the new line to denote different vertices.
Okay.
Yeah.
Thank you.
Mm-hmm. Yes. Okay. I'll be there in a second. Oh, sorry. So the explore.exe dot command, that's just to open up the folder in Windows Explorer, remember? From here you can open up the file in like Notepad just to make it a little bit easier to modify. You can do everything from the command line too. So if you do vim block mesh dictionary, you can use the text editor within the terminal, but that one's a little bit fussier to use just because you have to kind of go between editing mode and viewing mode and things like that. But I think I think it's a little bit easier just to use a notepad just because it's yeah, I think people are just more used to notepad, and you can use the mouse in here as well, which you couldn't in Vim. Yeah. Okay. What's that?
We're trying to copy the folder.
Oh, you have to make the folder. So let's backspace. Okay. So you made this channel flow directory inside your.
Oh, you didn't want to.
Right. Exactly. Yeah. So let's do this actually. So let's make it in the right folder. So let's do cd dot. Right. So that's going to get us out of this copy. So now we're in the OpenFOAM cases. You hit ls. You can see there's no channel flow because you created it actually one level above. So if you do make directory channel flow again inside this folder.
Yeah, do you know what that is? It's just basically, you know how like,
Yep.
like,
Sure.
you know how
Yeah, I can
this,
tell it. Yep, so now you have, now you can go back inside cavity and run this.
So it's just, CP cavity.
Yep.
Explorer just basically allows you to see it like
And then
like the CP instead.
effect.
Oh, okay. Well, besides that, you see, you have no view.
Yeah.
So. And then it's, you know, dot dot.
And you can use tab. Good. Good. All right, good to go.
All right, thank you.
Yeah. What's up?
I'm very excited.
Space.
We don't have to write no
Yeah.
more.
Yeah.
So now we
gotta type a lot more.
That's, you always gotta do something.
we thought we were in the clear.
All right, let's see what's the best way to do this. I do want to catch up just because let me do this. Just so the Ubuntu is actually, let me do this. Keep that there. Oops.
That would be what you should.
Guess that works. Okay, I'm gonna catch up a little bit. I'm probably not gonna be able to do everything just because you know, I'm kind of following along with you guys and just helping you guys out, but I will try to get as far as I can.
Oh, no, I'm chilling. It's because you put the first note there. Or so I thought they were in
Yeah.
Just so, because I'm from. Is there a reason why we edited in the actual block mesh dict in actual like?
In the terminal? You definitely could. It's just that in the when you're using the terminal text editor Vim, you can't use the mouse, and so you have to kind of use the arrows to go up and down. So it's just a little bit more cumbersome. And so just because you know you guys are doing a lot of typing today, and so I think just Notepad would just make it a little bit easier to do today.
Oh, and then it's just easy to.
Exactly. Yeah, it's easier to copy and paste in Notepad too.
Thank you.
I haven't done it on how you're doing it.
Mhm.
Is it kind of the same thing, like you have to press I to edit?
Yes. Yeah.
Okay.
Yeah.
And then to save it, you have to put the colon.
Colon X. Yeah.
Colon X.
From viewing mode.
Is there a way to exit it without saving it?
There is. I actually don't know the command for that though. But it's so Vim actually has a lot of commands that you can do from the viewing mode, and one of them is to exit without saving, but I'm not sure exactly what that command is. Yeah.
I'll decide.
Yeah, that's ChatGPT will tell you what it is. Yeah.
I do that pretty once I graduate, I'll cancel it.
Might get for your job.
Yeah, you're right, you're right.
Make your job pay for it.
Yeah.
If you don't mind, you scroll up a little bit so I can see point.
Point. Oh, yes, yes. Mm-hmm. And remember, if you're done typing out all the vertices, definitely feel free to move on. But I just want to make sure that everyone's kind of on the same page. So I'll probably move on maybe in about 5 minutes. I'll give you guys a bit more time to start typing this out. Seems like everyone's kind of at least on this part here where they're typing the vertices, which is great. Um, yeah. So 5 more minutes and then we'll move on. Yeah, don't forget the second set of 20. So remember, you need 40 overall. But if you kind of were just kind of watching what I did, once you type the first 20, you can just copy and paste that same list, except just change the z coordinates slightly from 0 to 0.1. And then make sure to update the indices as well. So you should have indices 0 through 39. So counting the 0 with 1, that is 40 different vertices. Okay.
So copy and paste is the same as I.
Yep. So if you're in Notepad, you can just use Control C, Control V. That's perfectly fine. That's part of the reason I prefer Notepad today, just because it makes things a little bit easier.
So, oh, like let's say 0.
Hmm.
You're not using commas to differentiate like text lines.
Right. Yeah. So right. So I'm just using spaces. Yeah. So OpenFOAM actually just uses spaces to denote kind of the different the different coordinates. Hmm.
I'm over here.
I think it should work with commas too, but I think spaces are more traditional. Yeah. Oh, I haven't tried with commas. My intuition says it should work with commas. That's how these things would work. But if it doesn't, then we can go back and delete them.
Right, did, I wanted to copy and paste, is that possible? You have to type more.
It is possible. It's just yeah, because with Vim you technically don't have a mouse. That's the so it's much harder to kind of highlight and then copy and paste.
Oh.
Yeah. But some command terminals will let you kind of highlight text and paste it with the mouse. But for the Windows Ubuntu, I don't know if it allows that. Yeah. Okay, all right. So how's everyone doing? Everyone got the at least the first 20 vertices down? Okay, good. Okay, one last thing we'll do before we move on, and I was having a hell of a time developing this activity because I forgot this, but um, this command up here. So you'll see that right above your vertices there is kind of a command in Block Mesh Dictionary that says convert to meters. We had this at zero point 0.1 last time because we wanted to convert it to basically not even centimeters, the one that's above centimeters. But we want to just work in just plain SI units here. And so instead of 0 0.1, we're going to change our conversion factor to 1.0. Okay, so make sure you do that just to kind of make things a little bit easier later on once we're applying boundary conditions and the like. Okay, so make sure your convert to meters is 1.0. It's easy to miss. I try to kind of highlight in a box here, but make sure you have that there. Okay. Okay. All right, so the next part that we need to define here are your mesh blocks. And so this is where we're going to define basically the amount of elements or the amount of cells that are going to be in our mesh. And it's going to be an important part for us to define our boundary conditions as well. Okay, so if you scroll down the document, you'll see that I have the exact same geometry, but I've kind of differentiated it a different way. So now you can see that we have these 10 blocks here. So starting with block 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And so those are going to be the blocks that we're going to define for our mesh. Okay. So if you remember from activity 1, right, we're going to be working under this section here in Block Mesh Dictionary called blocks. Okay. And we need to define the blocks for our mesh. Okay. So the way it works is like this. And so basically you're going to have 10 different lines here. So they're all going to start with hex. Okay. So hex, 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 right? So on and so forth, right? Where each line here is going to define the kind of the vertices and the number of cells for each block here. Okay. Okay. So the way it works is like this. And so you're going to start each line with hex. The next set of things you're going to have in parentheses, this is the list of vertices that define that block. Okay. So for this first block right here, we're basically going to define the vertices that go around this block plus the vertices that are behind it. Okay. So if you look at this block here, so this block 1, you can see that we start at vertex 0, right? And this is important. So we need to proceed counterclockwise around the block here, right? So we're going to go from vertex 0 over to vertex 15, up to vertex 2, over to vertex 1. Okay. So that's going to be the first 4 entries in our list here. So we're going to go 0, 15, 2, then 1. Okay. Then we want the exact same vertices, but behind. Okay. So I don't have the vertices, 20 through 39 here, but just imagine that they are just in front of these ones here. Okay. And it's actually very convenient here that there are exactly 20 vertices because in order to get the corresponding vertices for behind, you just add 20 to the ones here. Okay. So I'm going to copy this exact list here. So I'm going to copy and paste, right? So that's going to be our second set of 4, except I'm going to add 20 to all of these ones because those are the matching vertices on the behind our current set. Okay. So instead of 0, 15, 2, 1, we're going to have 20, 35, 22, and 21. Okay. So that set of 8 right there defines the block that we're going to use to define that mesh, that part of our mesh. Okay. Okay, so the next parts here is we have 3 numbers in another set of parentheses. This defines the number of cells in each direction. And so this is saying that we want 40 cells in the X direction, 40 cells in the Y direction, and 1 cell in the Z direction. Okay. Remember, even though this is a 2D simulation, we do still need three-dimensional elements. But in the Z direction, we're only just going to put 1 element. Okay. And then the last 2 parts here, you just kind of keep them the same. So we're not going to do any mesh grading. We're just going to kind of keep that at in the standards. We do simple grading 1, 1, 1. Okay. Okay. So what you need to do here is that you need to define your 10 mesh blocks here. So you should have 10 entries, right? Hex, hex, hex. Can't even count here. 1, 2, 3, 4, 5, 6, 7, 8. 2 more. Hex, hex. Okay. And you're going to list the vertices in the correct order for each of the blocks here. Okay. So just like the previous part, I've gone ahead and kind of numbered this for you. But it's going to be up to you to kind of type the vertices here. Okay. Now the ordering is very important here. So if you don't put the vertices in the right order, you are going to get an error when you try to mesh, right? And so you need to make sure that you proceed in a counterclockwise direction. Okay. It doesn't matter where you start, so you can start at any point within the block. So for block 2 here, right, let me kind of clear these drawings here. So for block 2, you can start at node 15, you can start at node 16, 17, or 2, right? So where you start doesn't matter, but you have to make sure that you proceed in a counterclockwise direction, okay? All right, and then for every mesh block, we're just going to use the same mesh, and so we're going to do 40 and 40, okay? So go ahead and work on that. And just remember, keep in mind of the vertex numbers here. I mean, it's in the figure here for you as well. And then just make sure you define the mesh parameter. Questions?
Does it matter if to go like 1 to 2 to 10 to 9?
No, it doesn't matter. You can define the blocks in whatever order that you want. I just have kind of a default numbering there, just to kind of make things a little bit easier. But yeah, but for the blocks, it doesn't matter. You can go in whatever, I just have them 1, 2, 3, 4, but you can go 1, 2, 10, 9, whatever order that you want, for that one. These matter a little bit less than the vertices. Um, yeah, I just have a default numbering there, just to make it. Mhm. Okay, so I'll give you guys maybe like 10 minutes to work on that.
Uh, the top part, include the space under it, it's like, that's like the cell, so make sure like, okay.
Yes. Yeah. All right, how's everyone doing? Good. So with this part right here, I will warn you that it's as I was making this activity, and I told myself I don't know if I was just being, I was just lack of sleep, but you will probably make some mistakes here, and unfortunately it's hard to tell kind of when if you made a mistake or not until we kind of reach the end. But just be aware of that. And so the most common mistake that you'll find here is that you put the vertices in the wrong order. So you either went clockwise or something like that. Okay. So later on, when you go to run block mesh, you might get an error that says that your mesh block is inside out. Okay. And so if it's inside out, then that means just check and make sure the order of the vertices is correct, based on the counterclockwise direction. Okay. And one thing I just noticed too, so one thing that's useful about OpenFOAM is that it'll tell you which block is the problematic one. And so if you have one block where there's an issue, it'll tell you that there's an issue with block 3 or block 4, something like that. Okay. So this is where the numbering is important because, if you do the numbering is kind of the same as I did here, it'll help with the debugging. But I just realized just now that OpenFOAM actually starts at 0. And so, this first block that you have here, just like at the vertices, this is actually going to be block 0. Next one's going to be block 1, 2, 3, so on and so forth. So, you would basically have to subtract 1 from each. If you're using the same numbering convention that I am, you basically have to subtract 1 from each one. So just be aware of that if you're going to be debugging and you're not sure what the number is. Okay. Okay. So with that said, I do want to make sure we kind of get through everything today. So let's go ahead and move on. So the next part here is actually going to be the most time consuming, because this is where we're going to define our boundary patches. Okay. So this is a part in activity 1 that we mostly kind of ignored, but this part here we're going to use a lot. Okay. So basically what we're going to do now, or the point of what we're doing now, is we need to define different parts of the exterior of our domain here, just for the sake of applying boundary conditions. Okay. So we're going to be defining different parts of our domain here, giving them names, so that later on, when we define our U file and our P file, we can then define boundary conditions on them. Okay. Okay, so for instance, let's kind of scroll down here. Okay, so you can see this is the last section of the block mesh dictionary file, but it is also the part we're going to spend the most time on. Okay, okay, all right. So basically, we need to define blocks like this, right, or sections of code like this that define our boundary, not our boundary conditions, but our boundary sections here. Okay, now for this particular model, we have 4 different sections. And so we have one section that's going to define the inlet. Okay. So remember, if you go back to the figure that showed our results here, we have flow coming in on the left side. We have flow exiting the right side. We have walls all the way around. And remember, since this is a 2D simulation, we have the special front and back empty parts of the domain as well. Okay. So that's 4 different types of boundaries that we need to specify. Okay. Okay. So remember, the way that these boundary patches work is that we need to define all the faces that comprise that boundary. And a face is comprised of 4 different vertexes. Okay. Now, all these right now, these are not gonna apply to our model just because these are copied just straight from our cavity. But let me go ahead and show you what it would look like if we were to define the inlet. Okay. So I'm going to change the name of this first boundary patcher to inlet. Okay. Right. So that means we're going to be defining the type and the vertices that comprise that inlet face. Okay. All right. So next thing we're going to do is we're going to change the type, just because the inlet we're going to be specifying a velocity, and so instead of a wall type boundary condition, we're going to change this to a patch. Okay. So that patch is kind of the most general type of boundary that you can have that lets you specify different values of velocity and pressure. Okay. And then the last thing we're going to do is we're going to define the vertices that define that inlet face. Okay. Now let's go back up here. Okay. So we know the inlet is going to be comprised of this. We know the flow is going to come in from here. Okay. But, just from our figure here, from our 2D figure, we only have 2 vertices here, 0 and 1. Right. But remember, there is another set of vertices that are right behind here. Right. That I couldn't draw just because I'm not skilled in MS Paint, right? But remember, the vertices behind here are offset slightly in the z direction, and their vertex numbers are 20 plus whatever here. So there's another vertex here, 20, and another vertex that's connected here, 21. Okay. Okay, and so if you connect those four dots here, right, we can see that we have a two-dimensional face that's going to define our inlet. Okay, so we need to define our four boundary nodes here inside that face there, right? And ordering here again does matter. And so the way that you do this here, whether you go clockwise, counterclockwise, that doesn't matter too much, but you need to kind of go progress in a continuous path around that face. Okay. So for instance, let's say that we're going to start at node 0. Okay. So from node 0, we're going to go up to node 1. Okay. So 0, 1. Then we're going to proceed to behind that one. We're going to go to node 21 from there. Okay. And then we're going to end at node 20. Okay. So that kind of progresses. I guess if you kind of look at it from that way, it is a counterclockwise way as well. But you could have easily gone clockwise as well. So you could have done 0, 20, 21, 1, exact same thing. Okay. Okay. So that defines our inlet. I'm going to show you how to do it for the outlet as well. But for the fixed walls and the front and back, that's where most of the money is going to be. Most of the work is going to be. But I'll show you how to do it for the outlet as well. Okay. So for the outlet, remember, we need to define this space here as the outlet. Let me go ahead and label these nodes. So this is going to be node 28, and this will be node 29. Okay. And so our outlet face here, which is going to be this set here. Okay. So let's go ahead and change this one here. So if you don't have a fourth one, so I think I have a fourth one here just because I was fiddling around with it in class. You can definitely create your own, right? So if you don't have a fourth one, so let's say that your code kind of looks like this right now. Definitely feel free to add another one here. Okay, so we're going to do outlet, curly brace, and curly brace. Okay. And we're going to type the exact same flags on the inside. So we're going to do type, right? Our outlet is also going to be a patch because we're going to define a pressure at the outlet. And then we're going to define faces here, open parentheses, close parentheses, and a semicolon, right? And then we're going to have our list of vertices that define this face here, right? And so just like we did with the inlet here, we're going to take our four vertices that define this face and progress clockwise in this case. We're going to do 8, 28, 29, 9. Okay, so that's how we define our boundary patches. So we have one for the inlet, one for the outlet. Okay. Okay, now for the fun part. So now we have to define the same patches, but for our walls and the front and back. Okay. Now, luckily for us, our cavity flow also had a fixed wall. It also had front and back. Okay. But because our geometry for activity 1 was so simple, there are very few entries here. As you can imagine, because our geometry here is a lot more complex, we're going to have a lot more entries in this part. Okay. Okay, so let's start with the fixed walls. So for the fixed walls, right, basically everywhere that the flow is going to be fixed, we need to add a boundary condition there. Okay. So let me go ahead and add some depth here. Okay. My mad drawing skills here. Okay. So this here is node 21. This is node 22. This is node 23, 24, 25, and 26. Okay. And of course, there's more, but I went through just that much. Okay. So each of those faces there, we're going to define a no slip boundary condition. Okay. So we're going to add that to our fixed walls list. Okay. And you can see there's a lot here. So there's, one here, there's one here, one here, one here, one here, right? You're gonna have another one here, another one here, 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 and here. And don't forget the blockage in the middle too as well. Okay. Okay. So let's start. I'll start the first few for you, and then you can kind of fill in the rest. Okay. Okay. So the first fixed wall here. So the first fixed wall, we're going to go along this surface here. So it's going to be 1, 21, 22, and then 2. Okay. Okay. All right, the next fixed wall patch is going to be this vertical one here. So we're going to 2, 22, 23, then 3. I'll do one more for you guys as well. So we'll do this top one here. Okay. Okay, so this would be 3, 23, 24, and 4. Okay. All right, and then you can kind of keep adding to that. All right. So let's count them up. Let's see how many faces that you need for the fixed wall. So you need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and don't forget the blockage in the middle, 15, 16, 17, 18. So you should have 18 faces here for the fixed walls. Okay. Okay, so once you guys get started working on that, if you're confused about kind of what the 18 faces are or what the verses are, definitely raise your hand. We are running a little bit short on time. I think what I'll probably have you, I think probably what we'll do today is we'll kind of just get through, kind of changing all the settings. And then we do have some stuff to talk about with the post-processing, but I think we'll do that. We'll do that next time. Okay. Okay, but for now, go ahead and start. Go ahead and start adding faces here. So remember, you should have 18 under fixed walls. Okay. And I'll add a few more just so you can have for reference as well. Okay, and then just to show you that the order doesn't matter, I'll do one like this: 5, 6, 26, 25. Okay. Okay, so what I have here is basically the entire upper half here. So these are the first 6. 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5, 6, 7. Missing one. 1, 2, 3, 4, 5, 6. Oh, I forgot 6, 7. That wasn't on purpose. I swear. There we go. Okay, so I did the first 7 on the top for you. There's going to be another 7 on the bottom, and then there's going to be a 4 of them for the blockage in the middle. Okay. All right, so I'll give you guys 5 minutes to work on that, and then we'll talk about the front and back. Yeah, exactly. Yeah. So remember, to get the nodes in the back, you just add 20.
Okay.
Yeah.
Thank you.
Mhm.
The
Again?
internal ones have those slopes as well.
Exactly. Yeah. Yeah. So for some of these internal ones, we like 17, 18, 38, 37. Yeah. Mhm.
Like, they're actually, they're counterclockwise.
Yeah. Yeah. So for this one, it doesn't matter too much. Yeah. Okay. All right. So once you're kind of done with that, we can go ahead and move on to the front and back. Okay. Now, this one there will be a lot in here, just because we need to define basically every patch here. So remember, the front and back, these are basically the patches that are going to be parallel to your XY plane. Because essentially, we have a 2D simulation here, but since OpenFOAM only works in 3D, remember, we kind of put special boundary conditions on the parts of the domain that are the front, literally the front and back of what we're looking at. Okay. So luckily, we can use the same name as our cavity, so we can define them as front and back. Okay, they're going to have the same type as empty. So the only difference here is that the vertices that we're going to use to define the faces are going to be different. Okay. Now I'll give you the first few. Right. Nice on the nice side is that you're basically going to define one front and back patch. We're going to find two actually per block. Right. So for block one right here, you're going to have the patch that's in the front and the patch that's in the back. Okay. So for block one here, our first patch, we'll do the front first. And so we'll go 0, 1, 2, 15. Okay. So that's going to be the first patch. And then we're going to have the patch that's going to be behind it. Okay. So it's going to be the exact same numbers, but we're going to add 20 to all of it. So it's going to be 20, 21, 22, 35. Okay. Now, if you notice that these patches, unlike all the previous ones, these patches are only going to stay within that plane. Okay. So if you count them up, you're going to have basically two patches per block. There are going to be 20 patches or 20 faces in this section here. Okay. Okay. So two per block. And so, I'll do block two for you as well. Okay. So for block two, and by the way, feel free, if you don't have to have them all consecutively line by line, you can add kind of extra spaces here if it'll help with the organization. Okay. So in other words, this is going to be block one here. Okay. So for block two, let's do 15, 16, 17, and 2. So that's going to be the front. And then the back is going to be the exact same numbers, but added 20. So 35, 36, 37, and 22. Okay, so this is block two. Okay. Okay. So I'll give you guys a couple minutes and just to mostly just kind of get started with that. I know probably it's going to take more time to type it all out, but I did want to talk about the rest of the activity today. Um, just so that you're kind of in a good spot. We'll talk about the post-processing stuff next time, but I at least want to get you to a point today where, if you were able to kind of keep up and type up all the vertices, you can at least run the simulation and then kind of see the results. Okay, so I'll give you guys just a couple minutes. I'll call it at 5:05 to kind of type those vertices. Okay. Yes.
move it over,
Mhm.
because it's like an in-between spot of like the one tab and two tabs.
Yep.
Is if I hit two tabs and then write it, it's fine.
Yeah, it's fine. Yeah, the tabs, the indenting here is just for organization, but the code actually just ignores them.
Oh, really?
Yeah.
Okay.
Okay, so I realize you guys are probably still typing just because there's a lot of vertices to type in there, but I do want to move on. But hopefully you guys are getting the sense of kind of what needs to happen in this part here. Okay. Now to run the simulation, there are a few more steps. Some of them are very small, but some of them are medium, I would say. So this is definitely the hardest part of the activity for sure. Defining your geometry, defining your mesh and the boundary patches. Okay. But this is the last thing that we do in block mesh dictionary. So, make before you exit, make sure you save. So Notepad member doesn't do that automatically. So go ahead and save it. I'm going to go ahead and close it just so that we can kind of go through the rest of the activity. I'm just going to kind of talk through it. But just know that the activity document, the PDF here, also kind of goes through everything as well. Okay. Okay. So when you're done modifying your block mesh dictionary file, you can go ahead and create the mesh. And so just like in the first activity to create the mesh, back in the command line, back in Ubuntu, you're going to run the command block mesh. Oh, you're not going to do it from the system folder. So make sure you're in your default channel flow folder, right? So when you hit ls, the only things you should see is just 0, constant, and system. Okay. So go ahead and type the command block mesh. If I run this right now, it's going to have an error for me just because I didn't finish modifying the file. But if you did everything correctly, then this should run and should produce your mesh. Okay. I will say, unless you are an OpenFOAM savant, you're probably going to run into some errors, and so don't be alarmed, don't be frustrated. It's normal. I think when I was developing this activity, I think I ran to maybe like 70 or 80 errors in total when I was developing this file. So hopefully you guys won't get up to that number, but you guys probably run some errors. And so in the document here, I do have some common errors that you will find both in the block. You're probably going to have errors in either the block specification or the boundary patch specification. So make sure you read the document here to kind of tell you kind of what the errors mean and how to fix them. Okay. Or of course, you can always just email me or come and ask in office hours. Okay. But if all goes well, you can actually check your mesh before you actually run the simulation. So you can run Parafoam and you can check your mesh just to make sure that it looks okay. So it should look something like this. And I realize I didn't take the best screenshot. It should probably be zoomed in a bit more, but you should get a pretty decent looking size mesh here. Okay. Okay. So once your mesh is specified and fixed, there are a couple other things that we need to do. Okay. So first thing is going to be a very small thing is that we're going to change our simulation to laminar flow if it's not already. Okay. Okay. So back inside our Windows Explorer here, or you can do this through Vim, same thing. I'm going to go inside the constant folder. And inside the constant folder, there is a file called momentum transport. Okay. So I'm going to go ahead and open this, and let's go ahead and open it up in Notepad. Okay. Question, yes.
To save and exiting then of semicolon.
So semicolon X.
Gotcha.
Yeah. All right. So under momentum transport here, this is a very short file, and we're just going to be making kind of one pretty small change. Okay. So inside momentum transport, we're going to change our simulation type. So if you remember from activity 1, the default simulation type in OpenFOAM is called RAS, which stands for Reynolds Averaged Simulation. Okay. And so that basically allows you to run some very basic turbulence modeling. But for our case here, the turbulence is actually going to add a little bit too much complexity. And so instead of RAS, we're going to change our simulation type to laminar. Okay. So you basically just change RAS to laminar. And then you're going to delete this section of the code here that has to do with RAS. Okay. Because that section of the code there specifies the settings for RAS. But if we're not running an RAS simulation, then there's no need to specify the settings for it. And so once you change the simulation type to laminar, go ahead and delete everything else in this file. Okay. So besides the header here, you should literally have just one line in this momentum transport file, which is just simulation type laminar, semicolon. Okay. Okay, so let's go ahead and save that. So hit Control S, or if you're using Vim, you can do Control :X. Okay. Go ahead and exit out of there. Right. And the next thing that we're going to do, let me actually do this from the command line just so you can see. It's also a little bit faster. Okay. All right, so let me go ahead and clear this. Okay. Okay, so after we do that, we're going to go inside our zeros folder. So remember, zeros, our zero folder, this is where we're going to specify the initial conditions for all of our parameters. Okay. So the only two that we're going to be concerned about here is going to be U. U here is our velocity. Okay. And P, which is our pressure. Okay. Every other file here, epsilon, K, nu tilde, nu T, omega, these are all variables that have to do with the turbulence modeling, which we're not going to be doing here. Okay, so we're actually going to remove all of these files. Okay. Okay, so remember the command in Linux to delete files is rm. Okay, so we're going to do rm, and I'm just going to list out all of these file names here. So epsilon, K, nu tilde, nu T, and omega. Okay, so we're just going to delete all of it. Okay. You can also do this from Windows Explorer if you want as well, but it's just very slightly faster to do it from the command line. Okay. Okay, so after you run that rm command, you should just be left with a U file and a P file. Okay. Okay, so now we need to modify this U and P file to specify our boundary conditions. Okay. Okay, so I'm going to do that just to kind of keep things consistent today. So let's do that from the Windows Explorer, right? So let's open up the U file first. Okay, so let's open that up in Notepad. I'll bring this here just so you guys can still see the command line. Okay. Okay, so we need to specify our boundary conditions here. Okay, so first thing we're going to do, right? So we have this this file here, this section called boundary field. So we need to have different sections here to define the boundary conditions for each of the boundary patches that we have. And remember, we had 4 boundary patches. So we had our inlet, we had our outlet. Okay. And if you don't have a 4th section, feel free to make one. Right. So we have outlet and make the curly braces. Okay. We're gonna have a type here. Okay. And we have our fixed walls in front and back. Okay. So luckily for us, in this case, our fixed walls in front and back are going to have the exact same conditions. So our fixed walls are going to have a no slip type, and our front and back is going to be an empty type. Okay. So for our inlet, we're going to specify velocity. I believe it's just a velocity of 1 in the x direction. Actually, it's going to be 0.5, excuse me. Okay. And so our velocity at the inlet is going to be 0.500. So that specifies a velocity of 0.5 meters per second in the x direction, 0 in all the other dimensions. Okay. For the outlet, okay, the outlet, we're going to specify a special type of boundary condition called 0 gradient. Okay. So that basically just means that we're not going to specify a velocity boundary condition on the outlet. Okay. We are going to specify a 0 pressure, but for the velocity, we're going to say 0 gradient. Okay. Okay, so go ahead and save that. And then we're going to do the same thing in our P file. So go ahead and open up the P file in Notepad. Okay. And we're going to do this very quickly here. Okay. So for the inlet is going to have a 0 gradient in terms of pressure because we're not specifying a pressure at the inlet. We're going to make another entry for the outlet here. Curly braces. Okay. Our type is going to be fixed value. Okay. Okay. Right. And then the value here. So for our outlet, we're going to define a 0 pressure outlet, which is very typical for internal flow. So our value here is going to be uniform, which means that we're going to specify that boundary condition valued uniformly across the entire surface, and 0. Okay. All right. And then for fixed walls and front to back, those are also going to be the same. Okay. Okay. So I know I kind of ran through that very quickly, but all of that is here as well. Okay. So definitely make sure that you kind of check the PDF here. And after that, you should be ready to run the simulation. And then what we're going to talk about on Wednesday is that, I'll go ahead and kind of finish the implementation on my end, just in my spare time. And we'll talk about some of the post-processing that we're going to do for this activity, because that's also kind of the new thing you're going to do here as well. Okay, so we'll spend maybe the first 15 minutes on Wednesday talking about that, right? All right, any final questions before we end it for today? Okay, questions?
Just in terms of what we should have prior to like us next to the house, should have 18 faces for the typed wall, 20 faces for front and back.
Yep.
One for move, wall 1 and wall 2.
So one face for the inlet and one face for the outlet. Yeah. Mhm.
And then was it a 10 foot block?
Yeah, 10 blocks. Yes.
And then the 40 vertices.
Exactly. Yep. Mhm. Okay. Yep. So I apologize for kind of going over a little bit. I know I kind of rushed to the boundary conditions at the end too. But that's the activity. And so, definitely go ahead and feel free to kind of go at it. If you have any questions, definitely you can always ask me. So thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you on Wednesday.
Sure.
Yep.
I saved this and that would explain this. Sure.
Yes.
Okay. Right file. Save as.
You can just hit save, because it's already saved there.
Okay, save these one.
Oh, sorry.
I wanted to shoot myself.
I think so. Trying to get to that. I think.
First, I'm gonna come.
I'll go to that.
Yeah, so you want to make sure that you save it.
I'm so impressed watching the highlights for the update.
Like, I knew it'd be hard, it's just the way we play. I don't mind leaving. I don't know, hopefully. Like, that's the one I should, just because we have such a gap. Even if it's like, we'll give us an. But. Yeah, lose my mind. I don't know what's the. And then Champions League, I think.
We know what.
They might lose some or. We might tell us that. They might say.
Three things that.
Oh, it's
so
gonna
happened that
we were
talking.
We had played the hell of me.
Okay, so this is your channel.
One of those three,
Then just copy that block.
Then you can have
There, you can place.
Yeah, it's not. Drop it in there and.
But
I think.
Yeah.
So we have. Let's say we scored.
You can open up the.
I don't think that would.
Oh,
yeah. Then.
And then go to your OneDrive, get that block mesh dictionary file, and then file you edit it. Yeah, when you're modifying things from the pad next time, you'll have to say that. If it's like regular save, so we'll save it as.
Okay.
Yeah.
Thank you.
Yeah.
Well,
Don't even worry about it. It's just like.
Hey, David, what's up?
I was having a good time right now.
So I have this.
Okay,
I don't have, this is lifted directly from the offer letter.
Okay.
I wasn't sure what else to put, because I really have nothing else.
Okay, this is good.
Because I don't know exactly what we'll be doing,
Mhm.
because they haven't given us that information yet.
Gotcha.
So like I said, I just lifted that directly from the offer letter.
Okay.
Will that work? Cause I register a week from Wednesday.
Yeah. So for this one, it's not like there are limited seats in 598.
Yeah.
Basically, when you submit this, we open up a spot for you.
Oh,
And
okay.
so, there's actually most people actually submit this the first week of the fall semester. So
Oh.
you're actually like 7 months ahead of
Oh,
time.
okay.
But I mean the sooner the better.
Yeah,
So we can try this and see.
okay. The other thing is, I know it's typically 2 semesters, but this is literally the only class I have left.
Okay.
So I was gonna try and get it done in one.
Okay.
I talked to Dr. No, and he said it's possible.
Okay.
Um,
We'd probably have to start over summer then. Probably.
well, I'll be in Cleveland over summer.
Oh, okay. Okay, I see. So you're gonna be going to Cleveland, get the data for this over summer, and then come back in fall, and then right.
As far as I'm aware, that's how it's
Okay.
gonna be, yeah.
Okay, yeah, that's totally fine. So let's yeah. So go ahead and so the department actually likes to keep this all digital.
Okay.
So go ahead and send me this because that still has kind of the fields here that we just
Sure.
click and sign.
Yeah.
So go ahead and send this to me. I'll go ahead.
Well, these ones don't have them to sign, I don't think. I think everything here and the dates, but not this.
Oh, really?
That's why I printed it out.
Oh, okay. Go ahead and send me what you have here. I can modify to add the signature.
Okay.
Yeah.
Okay.
Yep.
Thank you.
Mm-hmm.